So let's talk about translation and rotation matrices. Keep in mind, a transformation is defined as making a movement in space, which means we are combining translation together with rotation. So the homogeneous transformation, by definition, is going to be R0 over here, D over here. This one is 1. So this one over here is defining the rotation. This one over here is defining the translation. For translation, pure translation, it means that we do not have any rotation. It means that my R is going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. What does this mean? It means that our angles along x direction, y direction, z direction, they are all 0 degree, which so that we can have our matrix look like this one, which is an identity. If we are talking about rotation, pure rotation, it means that my D is going to be 0, 0, 0. Our matrix is determined by theta, phi, and psi, my rho, yaw, and pitch. So if we can understand what's going on over here, it should be pretty straightforward for us to generate the homogeneous transformation matrix. So let's talk about one example. Let's say I have 3 movements. The first one is displacement, the second one is a rotation, and the third one is also a rotation. So let's draw everything on a 3-dimensional space and see what's going on. So I got x naught, y naught, and z naught over here. The first step is displacement or pure translation, and it's moving from original coordinate to 4, -3, and 7. So it's going to be moved to this location. So my new coordinate system is going to be moving from x naught, y naught, z naught into this position. Let's change my color so it will be easier for us to visualize what's going on. So I'll have z1, y1, and x1 over here. Keep in mind my step 1 is translation. Which means my D is going to be 4, -3, and 7. My rotation from 0 to 1 is going to be an identity because my angle rotated about three individual axes are 0 degree, 0 degree, and 0 degree. So this is going to be my rotational matrix, and this one is going to be the displacement vector I'm going to use to generate my homogeneous um, transformation matrix. So the second step is change this coordinate and rotate about y-axis. So it's going to be rotated about this axis. Let's change the number, change the color again. Let's change that into this one. So after doing that, I'll rotate 90 degree. So it's going to be y2 is the same direction as y1, but this time my z1 has been changed from this direction into this direction, and x1 has been changed from this direction into this new x2 direction. So step 2, I'll have rotation. In this case, my d is going to be 0, 0, 0. Since I do not have any translation, but my r 1 to 2, that is something we need to identify over here. And y is going to be the same direction, so it is clear. The second column of this matrix is going to be 0, 1, 0. And x2 has been pointed to the negative z1 direction, so it's going to be negative 1 over here, and the other components, they are zeros. For the z direction, the z2 has been rotated from the original z1 to the x1 direction. So we're going to have 1, 0, 0 over here. So this is going to be my second step. The third step is that we're going to rotate the coordinate for another 90 degree, but this time it's going to be about x direction. So let's change the color again. So this time I'm going to rotate about z direction. So I'll have my new coordinate system. Clearly, z3 is going to be the same as the z2 direction, since we are rotated about z2 direction. So x2, x3 become this direction, and y3 becomes this direction, which makes sense, right? Because we are rotated everything for about 90 degrees, so it's going to be rotated from this direction into this direction. But how are we going to define our d and our r? So my d is still 0, 0, and 0, because we do not have any translation. But my r 2 to 3, we need to define. Because keep in mind, we are rotated about z direction, so it must be 0, 0, 1. Over here, the z direction is going to be the same direction. Let's get back to the previous page to see what's going on over here. And we are having x3 along the positive y2 direction, and we have our y3 direction along the negative x2 direction. So with those two pieces of information, we can write down the other 6 components over here. which is going to be 0, 1, 0, negative 1, 0, 0. Okay, so we finished our 3 steps and we got our displacement vector, we got our rotation matrix. So we can start to synthesize our homogeneous transformation matrix for individual step. Let's do that. So with that said, we should be able to come up with our H0 to 1 from frame 0 to frame 1. The transformation matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. This is my R. And my vector is going to be 4, negative 7, negative 3, and 7 over here. The fourth row over here is going to be 0, 0, 0, and 1. Nothing fancy. Since you know your D, your R, you should be able to come up with this homogeneous transformation matrix easily. Then we do the transformation matrix from frame 1 to frame 2. With the same idea, we are going to have 0, 0, 1, 0, 1, 0, negative 1, 0, 0. This is my R. My D vector, since we do not have any translation, so it must be 0, 0, 0 over here. The fourth row over here is standardized numbers. That is going to be 3 zeros and 1. That is transformation matrix from frame 1 to frame 2. If we want to do from frame 2 to frame 3, what are we going to have? We just copy this one and this one into this matrix. That is going to be 0, 1, 0, negative 1, 0, 0, 0, 0, 1. And for the vector, it's going to be 0, 0, 0 over here. For the fourth row, it's going to be 3 zeros and 1 over here. So now we complete the transformation matrix from individual frame to the next frame. If we try to convert or combine all those transformation matrices together and calculate the position from frame view from frame 0 to frame 3, it is going to be, it is going to be like this. So if you multiply this matrix with this matrix with this matrix, we are going to have our transformation matrix look like this. And with this transformation matrix, we should be able to convert the position from one frame to the other. So that is how we do that. If you only have a single joint and you have 3 different kind of movement, then we just multiply all individual homogeneous transformation matrix altogether, then we can find out what's going on after those 3 specific operations. But that is not good enough because sometimes we are looking for a system with more components. If we have, in particular, we are dealing with robotic device. So when we try to find out what's going on, let's say my observer is over here, but what I really want to know is the position at this point. This is my origin. So we might have to calculate the conversion from this frame to this frame, and maybe goes to this frame, then move to this frame, then move to this frame. We are having everything rotating, so there are some other things we might need to remember. The most important thing we need to know is that we would need to treat the whole kinematics as a chain, because you are not dealing with only single rotation or only single translation. You need to combine everything all together, while this specific robotic system has distance between individual joints. So that can make everything more difficult to calculate, but essentially we need to have all those information before we can find out how the robotic devices is moving with those variables. Okay, so let's do that. This specific calculation is actually called kinematic chains. When we are dealing with those kind of things, keep in mind we are having rotation, which is our theta. We also have our displacement, which is our d. And those two parts are our variables for a specific joint. We need to consider all of them all together, and we can start to do the we can find out the end position correctly. And also, if you try to find the transformation matrix from the very beginning till the position of the end effector, we will need to combine all the homogeneous transformation matrices altogether and generate a big matrix which is denoted by T. And if we are having something like this, we should be able to find out what's going on after a certain kind of trajectory has been adopted by the robotic system. Okay, so before we start to do everything, there are a few things we might need to remember. When we are dealing with um, all the matrices, this is my homogeneous transformation matrix. And from this one, this is actually from 0th frame to the nth frame. And this is my targeted frame. So this is the formula that we're going to use for calculating robotic movement, and how we synthesize the individual matrices using regular homogeneous transformation matrix and combine everything all together from the very beginning till the end. This is how we use the formula. If you just need to calculate from I frame to J frame, then this is the formula we're going to use. But essentially, those two matrices are identical. The only difference is that one starts from the zeros coordinate, and this one just calculate the kinematics between I frame to J frame. Okay, let's work on one of the example. So this one over here is the example from your textbook. So clearly, this one over here is fixed at the ground or some kind of fixed frame. And we attach a coordinate system over here, which is x naught, y naught, z naught, nothing fancy. And before it moves to the second frame, it will start to rotate, which means one of the variable you need to consider over here is theta 1, this one. And after it goes to this one, it will start to rotate about z1 axis with an angle theta 2. But x1 and y1 are not the regular x, y, z components we have um, at 0 spring. So we define another code. So when you are doing the calculation, you would need to be careful about the rotation part. For this one over here, it is using the same direction as x1, y1, z1 as the coordinate system over here which is x2, y2, and z2. But when this start to move, this joint over here is going to be rotated about z2 direction with a variable theta 3. Then this is going to be my n vector. So before we actually come up with the calculation, um, what do we need to do? So let's deal with first joint, link 1. This is my link 1. The distance between the frame 0 to frame 1, the distance is a1. So when we are dealing with something like this, this one over here is actually rotated about z naught direction. So since we know it's going to be rotated about z direction, the rotation matrix is straightforward to be determined. It is going to be having a 1 about z direction, and we have cosine theta 1, sine theta 1, negative sine theta 1, and cosine theta 1 in this specific matrix. And after doing that, this one is going to be changing its coordinate system from x0, y0, z0 into x1, y1, and z1. So we would need to find out how the rotation matrix is going to look like. But clearly, by comparing the old coordinate system and the first coordinate system, we actually find out x1 is along old y0 direction. So it is going to be 0, 1, 0. For the y1 direction, which is the second column over here, it is actually projected onto z direction. The other two directions, the components along the other two directions must be 0. For the third one, which is the z1 is along y0 direction. So this complete the rotational matrix from 0 spring to the first spring. If you do the calculation, you're going to find out this matrix is so the rotation matrix can be combine those two matrices together and and have the answer like this. Therefore, this is something we are having. Keep in mind, we are converting from the 0th frame to the first frame, which we have our D from 0 to 1 has a translation which is along Z direction, so it's going to be 0, 0, A1. And put them together, this is our transformation matrix. So let's deal with link 2. So link 2 is actually over here. If my distance or my length of the arm is this one, and the length between those 2 points is A3. So we have something like this. Again, we will need to consider 2 things. Rotation. This is rotated about the Z1 direction, so it will be similar to what we have in the previous part of this page. It is going to be cosine theta 2, sine theta 2, negative sine theta 2, cosine theta 2, 0, 0, 1, 0, 0 over here. So that is going to be the first uh, rotational matrix we're going to use with a variable theta 2. Now, we also need to know how the joint is going to change its directions. So we would do the matrix. We will need to make the matrix based on the technique we learned earlier. So x2 is going to lie along x1, so it's going to be 1 over here. The y direction of this joint is going to be the same as this joint, so it's going to be 0, 1, 0. By compare the z direction, it's going to be 0, 0, 1. So this one over here, since this one is multiplied by an identity, so the answer remains the same. Okay, we also need to define what is the distance. So we are going to have d2, d1 to 2. So if this one is rotated by an object and the movement is going to be theta 2. So if we need to find the position of this joint, it is actually A2 cosine theta 2. This one is going to be A2 sine theta 2. This is still 0. So we kind of complete the matrix of link 1 and link 2. Next thing we need to find out is link 3. This is pretty straightforward. We are having cosine theta 3 sine theta 3 negative sine theta 3 cosine theta 3 0, 0, 1, 0, 0 over here. For the D, and keep in mind the coordinate system does not change to another coordinate. it's not going to be rotated for 90 degrees for any reason, or going to be rotated about some other angles for a specific reason. Now, this time, it's going to be identical to frame 2. So we can just use an identity over here, which makes the calculation a whole lot easier. Okay, and go back to a previous page. This one over here, since we have F3 over here, then if we have one unit along this direction, the translation is going to give me um, so we can combine everything all together and come up with this one over here. So this one is going to be this is going to be the transformation matrix. So the T is going to be like this. So if we can multiply all the edge we just calculated, we're going to find out the answer over here is going to be a long calculation. And since this is a matrix, we'll have this one over here as my first homogeneous transformation, and the second one is going to be and it is going to be, and this one over here is going to be the vector, and this should be 0, 1, and the last one is okay. So this is going to be my H01, and this is going to be H12, and this is going to be H23. So if we multiply everything all together, this is a big chunk. It might be a good practice for you, and you should be able to find out what the answer is, or you can actually look up the answer in your textbook. Okay, so this will be the first part of Module 3. We're going to talk about forward kinematics data.